nice. I can go back. Yeah, perfect. Okay. So I'm going to present you the result of research that has been done in collaboration between Yale University and my company, Lagrange Labs, that is related to how to build a double action mechanism for efficient resource allocation in the context of a prover network. So let us unwrap that a little bit. The general plan, to put it in more layman terms, is to find a mathematically sound way to broker fair and mutually benefiting conditions in a market between sellers and buyers. And in this very specific case, given that my company is a company geared towards ZK proofs, but we do not want to do the proving ourselves because we are not AWS or GCP and we don't have any special hardware capacities. The goal is to basically put in a relationship between sellers, so people who have a lot of compute power and are ready to take on proving tasks, and buyers, which are clients that do want to generate ZK proof for whatever use case they are using. So this is a theme that has been quite widely explored in more traditional financial systems when it comes on to, for instance, market making or basic auctioning. But in this case, we have a very specific slight difference that is actually not really well covered in the literature. And this is a fact that for the clients, all of their offers are all or nothing, right? Like for instance, on the stock market, if you want to buy 50 shares of a given society at a given price, you would probably accept if I can only give you 45. But in this case, if you want to generate a ZK proof and you need a given amount of compute cycles, if I'm saying, okay, I can only provide you 95% of them, you're not going to accept the deal because you want to finish the proof. You don't want to have the computation stop in the middle. So this is where we are differing from the more classical application on theoretical exploration of the domain. So now to dive down a little bit deeper in the application of this system in our company, we are running a couple of prover networks that are running different proving systems for different applications, but all of them are following the same global organization. So we have clients. Clients are the people that want to have ZK proof run and proved and returned back to them. We have operators. Operators are entities that are running one or more on many computers, and they want basically to make a margin between the cost of exploitation and the money that they will get when they run the proofs. And finally, we have the auctioneer, and the auctioneer is ourselves. So we basically want to nurture the ecosystem that we developed, and we want to put these people in a relationship so that they can use our ZK systems. So this is the global overview, and now we will focus quite closely on how to have clients putting up offers with for a given amount of computation at a given price, and operators proposing proving computational power at another given price, and how to match between them. So to start with a little bit of definition, there is like the pentafecta of a good auction system that has been defined in the literature. And for a proving system to be efficient and to be smooth and for everyone to actually have an incentive to run into it, these 5 criteria have been retained. So you have the truthfulness. It means that every people basically taking part in the system do not have any advantage into lying. So it doesn't make any sense as you don't get rewarded, for instance, as an operator to overestimate your running costs. You have the weak group strategy proofness. Basically, if you are trying to conspire with a group of people to act on the prices, there will always be at least one person in the group for which it is more advantageous to leave the group rather than to maintain the clique and to maintain the conspiracy. Then you have welfare maximization. Basically, we want to extract the maximum amount of value for everyone. So we want to find the global maxima of value generated, which is basically paying as little as possible for the clients and getting as much money as possible for the operators. Then there is a weak budget balance criterion, which is saying that the auctioneer does not lose money, of course, because otherwise, if you're losing money, you're not really running a long-term system. And finally, you have the computational efficiency, which is not really a criterion, but more a limitation of the real world, which means that the algorithm must run in a polynomial time, which is a fancy way of saying that you cannot really find galactical algorithms that would take months or days to find the optimal solution to a given auction. That wouldn't be realistic. Now, the thing is that what the theory is headbutting against is that kind of problem, so the double auction mechanism problem, is actually very similar, and in some way, very similar to the knapsack algorithm, knapsack problem. So, what is the knapsack problem? The knapsack problem is what you hit when you are trying to fit all you can in the hand luggage that you can take on the plane, right? So you have a given luggage, you have a lot of stuff of variable sizes and weights that you want to take with you on your trip, but you are limited to, I don't know, 15 kilograms on a small carry bag. So what do? You have to find the optimal solution to take on as many items as you can while respecting the limitation of the knapsack. And this is a problem that is unfortunately NP complete, which means that basically if you want to find the optimal solution, you have to try every single other solution. So when you have 3 items, that's pretty simple. When you have 45 of them, your combinatorial complexity is already through the roof. And so that kind of problem is not really solvable on a maximal, global maxima in a reasonable amount of time as soon as you are living like the most basic of precincts. So what we are doing, because exactly the same limitations are applying to our system, which is some kind of a very complex knapsack. So what we are doing is that we will be basically loosening some of the criterion, and we will reach what I would call a tetra-and-a-half vector of a good auction. So we are keeping the same criterion, but we are going to change some of them. So for instance, the welfare maximization, which is the hardest one, instead of maximizing the value that is extracted from the auction, we are just going to make sure that it is positive. And too bad if that's not the optimal solution, but at least we will have a solution where everyone will be making money on the system as a whole will behave in a probably not optimal, but at least acceptable way. So following that, the global strategy that has been established is to define a parameterized family of algorithms. So basically, you take building bricks, and you will be building, according to a single recipe, an algorithm from all of these bricks. Then you will prove that this algorithm recipe is actually fulfilling the criterion of the tetra-and-a-half vector of the good auction. You will choose parameters that are adapted to the application, so you will change the little building bricks before running your recipe. And finally, you just have to cook that thing, and you get what you want for your use case. So here we are going to describe what are the parameters of the family of algorithms that we define in this paper. So the first thing that you need is a ranking that has to be consistent and monotone for clients and provers. So what this part of the algorithm do is that it will rank the offer from the provers and the offer from the clients in a way that will be used then by the other pieces of the algorithm. Then you must have an asymmetric composition rule, which will determine whether client-prover match, so whether a match between a given request for proof and a given offer for computation is actually useful or not. So for instance, you need to be sure that the computational power is bigger than what is required to run the proof. You have to ensure that the prices between the offer, between the bid and the offer are compatible, and so on and so on. You need an asymmetric composition between the clients and the prover. So this is the part of the algorithm that will be generating this matching to be accepted or rejected by the composition rule. And finally, you need a payment rule, which will be there to price the matches between the proof request and the computational power that has been offered by the clients. So in our specific case, the rule that we are using is that we are ranking the proof offer in a decreasing order of profitability for the prover, so that we are running first the one where the, let's say, cost by cycle is the highest. And for the prover, we are ranking them in decreasing order of computational power. So this way we have the biggest one running first and the smallest one at the end to take anything that couldn't fit in the biggest one. So what are the applications for that? So the problem, of course, is that this is a very nice and very fine theoretical design, but then you hit your head against the wall of reality, and this is exactly the thing that happened here. So for instance, the paper only defines what happened in a single round of an auction at a given point, but when you are running a prover network, then the thing must run in a continuous way, right? You have always incoming requests for proof, and you have always incoming machines on the operator side, or machine leaving, and so on and so on. So you need to introduce a dimension of temporality, which is not necessarily something that is trivial to do if you want to maintain the characteristics of the algorithm. So this is something that we are working on closely with our mathematical department. You have to, in some way, only let truthful partners within the double auction. So for instance, you don't want people who will provide you with computational power that will fail, or that will take a very long time to run proof, or that will have a lot of more technical issues. And this is not even talking about people that are actually trying to damage your model, but this is another question. You also need to implement sometimes client-specific criterions, because when you are interacting with other companies, of course, other companies won't always have a whole set of requirements that they will reveal to you in due time. And they will want, for instance, to favorize some kind of operators because they may have previous deal with them, or in any way. You have to, let's say, add all of this meta information within your system so that you can, let's say, satisfy the two parts in the business deal. You also have to discriminate between heterogeneous hardware. This way is a very big issue, of course, because in the real life, computational cycles are not all the same, right? If you have a proof that can either run on a GPU or a CPU, and you have proof that can only run on CPU, and proof that can only run on GPU, how do you balance all of that to maintain all of these criterions? Because, for instance, you cannot if you were to have completely separate queues for CPU and GPU, you probably would end up with some unoptimal use of the total compute power. If you mix everything together, then do you want to prioritize dual machines, or do you want to prioritize GPU machine or whatever? I mean, that's a very complex set of issues that are also quite interesting to solve, I would say, and sometimes, unfortunately, add another combinatorial factor to the final complexity of the algorithm, which ends up with something being close to, well, virtually unsolvable in a reasonable amount of time. And once again, you have to rely on heuristics to actually be able to address that kind of issues. So yeah, that was it. Thank you for your attention. I hope this gave you a glimpse on the technical difficulties and the challenges that come from taking a pure research paper and actually porting it over to a final product. And thank you for your attention.